Okay, in this video, we're going to see how to solve an active filter problem. We're going to look at this, we're going to turn it into phasors, we're going to find the transfer function, and then we're going to go ahead and graph that. So the first thing to do is convert things into phasors. So we have our V in here. We know the impedance for a capacitor is 1 over j omega c. Notice I didn't give you the value of the capacitance or the resistance. So that means we're going to leave things in terms of R and C here. And then we go ahead and finish our circuit here. And this is our V out. Now, in this particular problem, we always like doing node voltage at one of the terminals. In this case, we'll do it the plus. That's the one where the resistance and capacitor are hooked up. However, it's not connected to zero, it's connected to the output here. So that means if this is our V out, then by connection here, this is V out, and by ideal op-amp rules, this is V out. So then we're going to go ahead and write our node voltage here. The current going left is V out minus V in over 1 over j omega c. The current going down is V out minus 0 over R. The current going right is 0 because in an ideal op-amp, no current is going in the plus terminal. Now on this one, since we have a 1 over j omega c in the denominator, if you move to the top, it's just regular j omega c. And then if I want to get rid of the fraction here, I can multiply everything through by R as well. And I have j omega RC V out minus j omega RC V in plus V out equals 0. Go ahead and factor the V out on the left side. It would be 1 plus j omega RC. The other term on the right side, j omega RC V in. And now just by doing some division here, V out over V in is j omega RC over 1 plus j omega RC. So this goes ahead and gives us the transfer function, and it happens to already be in the right format where we want things with j omega times a constant and 1 plus j omega terms here. So what I'm going to do is I'm going to kind of start over with this and we'll draw the Bode plot. So we're going to go ahead and start over now. So our transfer function, h of j omega, was j omega RC over 1 plus j omega RC. I'm only going to do one thing here, j omega constant RC over 1 plus j omega over 1 over RC. The reason I did that is because we always want our factors as 1 plus j omega over omega naught. We need to know that omega naught, that break frequency here. Now, drawing our graph here, we see we have a j omega power in front here. Because of that, it's not going to start out flat. It's going to start out with a positive slope of 20 decibels per decade. And then we have this 1 plus j omega omega naught terms on the bottom. So that means once I get to that break point, it's going to have a negative 20 slope added onto it, which is going to cancel out the positive 20. So once I get to the point where it's 1 over RC, it's now going to flatten out here. And the only thing to worry about now is we have this RC term right here, but that's just basically our K term, right? And so that means we need our graph to be shifted up by 20 log RC. Well, normally, if we didn't have that, then at 1 we would be at 0, right? When we get to the first breakpoint here. You can look at this. If you plug in 1 over RC into the original problem here, what happens if you plug in that 1 over RC? then you'd get J times 1 over RC times RC over 1 plus J times RC over, sorry, there's a 1 there. 1 over that. It's going to be 1 over RC over 1 over RC. And all the RC sets are going to cancel out. And it's going to simplify down to just J over 1 plus J, which the magnitude of that would then be 1 over root 2 here. And if you did your 20 log 1 over root 2, you can find the value of this. And it's actually going to be negative, so my graph's not quite perfectly accurate, but that's fine. It doesn't really matter exactly what that value is at that point, but this is what we have here. So now that we have this, we can identify what type of filter this is. Well, low frequencies over here, they're going to have a lower output, and only when you get to high frequencies is your output going to be good. So this is exactly going to be a high-pass filter based on our graph there. Low frequencies have a lower output, high frequencies have a higher output, therefore it's a high-pass filter.